In computer science, the longest increasing subsequence problem is to find a subsequence of a given sequence in which the subsequences elements are in sorted order, lowest to highest, and in which the subsequence is as long as possible. This subsequence is not necessarily contiguous, or unique. Longest increasing subsequences are studied in the context of various disciplines related to mathematics, including algorithmics, random matrix theory, representation theory, and physics. The longest increasing subsequence problem is solvable in time O, and log n, where n denotes the length of the input sequence. Example, in the first 16 terms of the binary van der Korput sequence, 0, 8, 4, 12, 2, 10, 6, 14, 1, 9, 5, 13, 3, 11, 7, 15, a longest increasing subsequence is 0, 2, 6, 9, 13, 15. This subsequence has length 6. The input sequence has no 7-member increasing subsequences. The longest increasing subsequence in this example is not unique, for instance, 0, 4, 6, 9, 11, 15 or 0, 4, 6, 9, 13, 15 are other increasing subsequences of equal length in the same input sequence. Relations to other algorithmic problems. The longest increasing subsequence problem is closely related to the longest common subsequence problem, which has a quadratic time dynamic programming solution. The longest increasing subsequence of a sequence S is the longest common subsequence of S and T, where T is the result of sorting S. However, for the special case in which the inputs is a permutation of the integers 1, 2, n, this approach can be made much more efficient, leading to time bounds of the form O, and log n. The largest clique in a permutation graph is defined by the longest decreasing subsequence of the permutation that defines the graph. The longest decreasing subsequence is equivalent in computational complexity, by negation of all numbers, to the longest increasing subsequence. Therefore, longest increasing subsequence algorithms can be used to solve a clique problem efficiently in permutation graphs. In the Rubin-Saunay-Schoenstedt correspondence between permutations and Young tableaus, the length of the first row of the tableau corresponding to a permutation equals the length of the longest increasing subsequence of the permutation, and the length of the first column equals the length of the longest decreasing subsequence. Efficient algorithms. The algorithm outlined below solves the longest increasing subsequence problem efficiently with arrays and binary searching. It processes the sequence elements in order, maintaining the longest increasing subsequence found so far. Denote the sequence values as x, 0, x, 1, etc. Then, after processing x, I, the algorithm will have stored values into arrays, m, j. Stores the index k of the smallest value x, k, such that there is an increasing subsequence of length j ending at x, k, on the range Ka per mole currency I. P, k, stores the index of the predecessor of x, k, in the longest increasing subsequence ending at x, k. In addition, the algorithm stores a variable L representing the length of the longest increasing subsequence found so far. Because the algorithm below uses zero-based numbering, for clarity we pad m with m, 0, which goes unused so that m, j, corresponds to a subsequence of length j. A real implementation can skip m, 0, and adjust the indices accordingly. Note that, at any point in the algorithm, the sequence, x, m, 1, x, m, 2, x, m, l, is non-decreasing. 4. If there is an increasing subsequence of length I ending at x, m, I, then there is also a subsequence of length I1 ending at a smaller value, namely the one ending at x, p, m, I. Thus, we may do binary searches in the sequence in logarithmic time. The algorithm, then, proceeds as follows. P equals array of length n, m equals array of length n plus 1. L equals 0. For I in range 0 to n1, binary search for the largest positive JA per mole currency L, such that x, m, jx, I, low equals 1, high equals L, while lower per mil currency high, mid equals /2, if x, m, mid x, I, low equals mid plus 1, else, high equals mid 1. After searching, low is 1 greater than the length of the longest prefix of x, I, nu l equals low. The predecessor of x, I, is the last index of the subsequence of length nu l1, p, I, equals m, nu l1, m, nu l equals I. If nu ll, if we found a subsequence longer than any we've found yet, update l equals nu l. Reconstruct the longest increasing subsequence, s equals array of length l, k equals m, l, for I in range l1 to 0, s, I, equals x, k equals p, k. Return s. Because the algorithm performs a single binary search per sequence element, its total time can be expressed using big O notation as O, na log n. Fredman discusses a variant of this algorithm, which he credits to Donald Knuth. In the variant that he studies, the algorithm tests whether each value x, I, can be used to extend the current longest increasing sequence, in constant time, prior to doing the binary search. With this modification, the algorithm uses at most n log 2 n a n log 2 log 2 n plus o, n, comparisons in the worst case, which is optimal for a comparison-based algorithm up to the constant factor in the o, n, term. Length bounds. According to the Adesa-Sakir's theorem, any sequence of n2 plus 1 distinct integers has either an increasing or a decreasing subsequence of length n plus 1. For inputs in which each permutation of the inputs is equally likely, the expected length of the longest increasing subsequence is approximately 2/shn. In the limit as n approaches infinity, the length of the longest increasing subsequence of a randomly permuted sequence of n items has a distribution approaching the Treshire-Widom distribution, the distribution of the largest eigenvalue of a random matrix in the Gaussian unitary ensemble. Online algorithms. The longest increasing subsequence has also been studied in the setting of online algorithms, in which the elements of a permutation are presented one at a time to an algorithm that must decide whether to include or exclude each element, without knowledge of the ordering of later elements. In this variant of the problem, it is possible to devise a selection procedure that, when given a random permutation as input, will generate an increasing sequence with expected length approximately /2n. Variance bounds have also been studied, but exact variance asymptotics and limit theorems are still open. More precise results are known for the corresponding problem in the setting of a Poisson arrival process. See also, patient sorting, an efficient technique for finding the length of the longest increasing subsequence, Plactic monoid, an algebraic system defined by transformations that preserve the length of the longest increasing subsequence, Anatoly Vershik, a Russian mathematician who studied applications of group theory to longest increasing subsequences, longest common subsequence, longest alternating subsequence, references. External links, Algorithmist's longest increasing subsequence, explanation on Geeks for Geeks.